second round. يلا يا شباب. أنا أوكي. أنا دائما بفضل إنه إذا صار تصوير يصير تصوير لثاني محاضرة أو ثالث محاضرة على نفس الموضوع. لأنه sometimes I can see in your eyes مرات لما أحكي عن الشغلات إنه مش فاهمينها الشغلة اللي بعديها يعني بعرف نقاط الضعف سواء عندكم أو عندي. نبدأ بخبر اليوم. أنا عندي دائما أخبار لأنه أنا I follow the news so يعني it's exciting. So الخبر بحكي لكم إيش اليوم الصبح إنه scientists ب Dana-Farber Cancer Institute الموجود في نيويورك. It's one of the best cancer centers. They were able to identify patients with cancer with an accuracy. Listen to this and please react. Yeah, I'm not talking with an accuracy of 99.4%. Yes. So, not only that, like they were able to identify the site where the cancer is. أخذوا تقريبا 1500 واحد عندهم كانسر، عارفين إنه عندهم كانسر، و1500 واحد ما عندهمش كانسر، وعملوا شيء بسموه next generation DNA sequencing. ما حكينا عنه في الموليكولر. السنة هذه بس اللي حكيت عنه actually بالموليكولر biology. Next generation DNA sequencing is really fast sequencing لكل ال DNA. يعني إذا أخذت الهيومن جينوم بروجكت 15 سنة عشان يخلصوا sequencing of the human DNA. هلا with this technology, next generation DNA sequencing, they can do it in 3 days, 2-3 days, and they can finish it in 24 hours. Imagine إنه اللي أخذ 15 سنة هلا بياخذ 24 ساعة. So they did next generation sequencing لها 3000 شخص. عدد مهول هو صحيح. فعرفوا إنه يعني أخذوا عملوا comparison بين هذول healthy individuals والناس عندهم cancer, and they were able to identify biomarkers أو changes. وهي كانت epigenetic changes يعني changes بالmethylation والacetylation هاي الأشياء. mainly methylation of DNA. عرفوا إنه هذه هي الماركرز اللي بتحدد إذا كان عنده كانسر ولا لا وين هذا الكانسر. lung, breast, prostate, colorectal, stomach, whatever. Different types of cancers. So it's really amazing where we are heading. Okay. Let me just do a couple of corrections. جل ملا يخطئ. هاي السلايد عن بيروفيت كاينيز أنا I modified it راح أبعت لكم أنا إن شاء الله ب modified slide. Actually أنا صحيت على 1:30 بالليل. I couldn't go back to sleep. فمسكت الموبايل and I started reading about pyruvic kinase. لحد ما عزلته على 3 Anyhow, so pyruvic kinase basically إنه إحنا عندنا 4 isoenzymes produced from 2 genes. Each gene produces 2 isoenzymes. سواء كان splicing or something. Usually he has splice variants, RNA splicing. So the genes are PK, pyruvic kinase, LR. L stands for liver, R stands for red blood cells. And the other one is PKM2. طيب, فعندنا إذن a gene, PKLR, produces 2 isozymes, PKL for liver and PKR for red blood cells. And the other one, PKM2, produces 2 isoenzymes, PKM1 and PKM2. Okay? The difference is PKM1 is found in brain and muscles. PKM2 is found in all other tissues, including fetal tissues. So it is the fetal specific isoenzyme. And then we have PKL for liver, PKR for red blood cells. These two are allosteric. The other ones, the PKM isoenzymes, are not allosteric. The PKL and PKR are allosteric. So they are regulated by these, by phosphorylation, by ATP, acetylcoenzyme A, and so on, alanine, and the fructose 1,6 bisphosphate. Fructose 1,6 bisphosphate is the activator, and all of the other modifications or metabolites or factors are inhibitors. And I said that the fetal enzyme acid is more active, apparently, resulting in reduced level of intermediates, glycolytic intermediates. So I'll give you this slide. The other thing that I have to correct, and I mixed up different diseases with each other, is this here, related to this slide. Now, the idea with this slide tells you that it's the activity of the glucose 6-phosphate dehydrogenase that is reduced as red blood cells age. So as they become older, the activity is reduced. And this is, so notice that at 120 days, there's hardly any, in normal cells, hardly any glucose 6-phosphate dehydrogenase activity. So that goes well in line with the life of red blood cells. So it's really glucose 6-phosphate dehydrogenase that determines the lifetime of a cell, red blood cell. And that's the point. I think I said it wrong, it's related to the age of a person. No, it's related to the age of the red blood cells. So that's the correction. So okay, so let's move on. And I decided to give you a lecture, inshallah, on heme biosynthesis and degradation, and to talk about the different diseases in a bit more details. This topic is very relevant to all of us. So we need to talk in more details about it. Inshallah, it's not going to be an extra lecture. I still have this lecture, Metabolism of Iron. Next week I have 2 lectures. One would be on blood coagulation from a biochemical point of view, activation and regulation of different coagulating factors. And that will be on Sunday. On Monday, we'll have heme biosynthesis and degradation, inshallah. So I'm going to skip this. Okay, so let's talk about iron. Now, iron is very precious to the body. It cannot lose any iron. Very little iron is lost. But there's a fact that iron exists in 2 oxidation states, either in the ferrous or in the ferric state. So during this lecture, I'm not going to say Fe plus 3, Fe plus 2, or ferric ferrous. What I'm going to say is, most often I'm going to say plus 2 plus 3, iron plus 2 plus 3, just to be quick. So, but you need to know this is ferric, this is ferrous. So it is important for the function of many proteins, including hemoglobin, myoglobin, as well as enzymes like cytochrome P450s. So it's really an essential molecule. But there is a down point, and that is iron can be toxic. So it has to be, it should not be a free molecule. It has to be preserved, it has to be hidden within proteins. So this is the life cycle of iron. We'll start here. So if you look at it, actually there's little iron absorbed from food. The food that contains the most iron is, of course, meat, but it's lentils, the adas. It has the highest amount of iron. It's not spinach or pies. It does have some iron, good amount of iron, like not the most. So very little is absorbed of iron. But if you look at how much iron there is in our body, in a healthy body, it's about 4 grams, 3 to 4 grams. That's a lot. Very little is absorbed though. But most of it is preserved. Now, most of this iron is found in erythrocytes. Okay, about 2.5 grams is found. 2.5 grams is found in erythrocytes. Now, erythrocytes, of course, they die. You have cell renewal. Many cells are renewed every day. You have release of iron, and this iron must be recycled back into erythrocytes. Now, plasma contains also very little iron swimming in blood, about 4 milligrams. Most of it goes into the production of hemoglobin. Some of it goes into the production of other proteins like myoglobin and enzymes, cytochrome P450s. 1.5 grams are stored in ferritin, in liver mainly, and very little is lost. Okay? This is another important point. So let's talk about, this is all the information that I told you about. So, again, that's the one, okay. So let's talk about iron absorption now. So I'm going to focus on this figure, it's a nice one, and go into details. So the thing is, an important point is that in alkaline pH, iron is present as +3. In acidic conditions, like in stomach, it's present as +2. In order for it to be absorbed, it has to be in the +2 form as well. In order to be stored, it has to be in the +3 form. So the main cells that absorb iron, of course, is erythrocytes, and this is done via a transporter known as DMT1. DMT stands for divalent metal transporter. So it's not only specific for iron, but it can also transport other molecules like copper and zinc and cobalt, any +2 atoms, 2 molecules. So, but in order for this molecule to transport iron, the iron itself must be reduced. It has to be reduced from +3 to +2. Okay? And this is done by a membrane-bound enzyme, a reductase, ferroreductase enzyme. It reduces iron +2, and then it can get into cells. Great. Now, another source of iron is not only the free iron itself, but also iron in heme. So if you eat meat, there's a lot of heme, of course, and it contains iron. And so what happens is that this heme can be transported inside cells via a carrier known as heme carrier protein. Okay? So once it goes into the cells, iron can be released from iron. So in cells like macrophage cells, these are the ones that that destroy the unhealthy red blood cells. Hemoglobin is released, it gets degraded. Heme is released from hemoglobin molecule, and it can be transported into macrophage cells by a similar protein, carrier protein, heme carrier protein. So it goes into cells, and you have an enzyme known as a heme oxygenase. What it does is that it releases iron from heme. That's in macrophage cells. Okay, great. Now, there are different things. So we have now iron inside enterocytes, intestinal cells. Now, what happens then is that this iron has different fates. Fate number 1 is that it can be stored in ferritin. Okay? And this ferritin is a really large molecule, and iron can be stored right in the middle, in the core of this molecule, and about 4,500 iron atoms can be stored within this molecule. A lot of iron can be stored in ferritin. Okay? Now, the thing is, if ferritin in intestinal cells stays as is inside these cells, some of this iron can be lost Because you have cell shedding, you have cell renewal, you have removal of these cells. Okay, so this iron will be lost. So it has to leave these cells into the blood. Okay, and this is fate number 2. That is transport. It has to leave these cells, and it leaves cells by another transporter known as ferroportin. This is a very important protein. So the first one we talked about is divalent metal transporter. The second one that absorbs iron into cells. The second one is the ferroportin that transports iron outside of these cells. Okay? So ferroportin is an important protein. Now, once iron leaves these cells, it has to be oxidized into the +3 form, and it binds to a protein known as transferrin. Transferrin is an important protein. Okay, so and the oxidation of iron is carried out by an enzyme that is also bound to the membrane, known as a ferrooxidase. Okay, now in macrophages they also have ferroportin, and they also can kick iron out of the cells. But once they got out of the cells, they have to be oxidized, and they are oxidized by ceruloplasmin. This is one of those important plasma proteins that you learned about in Biochem-4. Okay, so there's a condition related to iron deficiency known as aceruloplasminemia. That is deficiency of the ceruloplasmin. Okay. So you have transferrin now. Transferrin carries iron, and it carries iron in blood. Now, transferrin itself is a large protein, and it can bind 2 molecules of iron. Yes? The heme itself, well, yes, some of it can be transported out as is, yes, but notice that there's a question mark about the mechanism of how it gets transported. يعني ما
الهيم بيطلع عادي ولا بيترك الحديد برضه ترانسفير؟
Then it can still bind to iron when it leaves cells. Yeah, but most of it gets degraded. Or most of it يعني gets.
البلازما بلاقي هيم عادي.
No, it gets degraded quickly. Remember, heme is hydrophobic, so it doesn't dissolve well in blood. Right? So no, it gets degraded quickly. هذا التوبيك إن شاء الله بنحكي عنه الأسبوع الجاي. Degradation. Okay. So transferrin is a large protein. It can carry 2 molecules of iron, so this is transferrin. You have one here, and the other one is right there. And it doesn't get really saturated. About the limit of saturation of transferrin is about 45%. So most of it stays unsaturated. About 1/9 of transferrin molecules can bind to 2 molecules, but both sides are filled. Most of it will have 1 molecule bound, and you also have 1/3 of these molecules having no iron bound to them. So 45% of transferrin would be saturated or bound with iron. So once it gets above that, if you have a lot of iron in the system, it can bind to other proteins. So this is known as non-transferrin bound proteins, or non-transferrin bound iron, if we're talking about iron that bind to other proteins. And this can be up to 75% of iron in the system, otherwise it would be free. And of course it's pathological in that case. So transferrin carries iron throughout the body, and it binds to a receptor on the cell surface known as transferrin receptor. Specifically, and it's not written in this slide, it's known as transferrin receptor 1, because there is another transferrin receptor known as transferrin receptor 2. So it binds to transferrin receptor 1, they get activated, and you have receptor-mediated endocytosis, meaning that the whole receptor goes into the cells by mechanism of endocytosis. So it goes into, it merges or fuses with vesicles that have a pH of about 6, and then which are early endosomes, and then they fuse with late endosomes having even lower pH, a pH of 5, and that results in release of iron from transfer. So now you have iron inside these in these late endosomes, and the receptor is punched out or off the vesicle, or it goes back into the plasma membrane so that it can bind to another transfer molecule, and iron can be transported or can leak out of these vesicles. Now cells do have iron and they can do whatever they want with it. Liver cells can store iron with ferritin, so the main storage place of iron actually is the liver, or molecules can use it for their enzymes like cytochromes or whatever, myoglobin or whatever. Okay, so this is now, so we talked about the number of proteins now, okay? The DMT1, divalent metal transporter, the ferroportin, ceruloplasmin, the reductase, the oxidase, and the transferrin receptor 1. Okay, so how are these proteins regulated? They are regulated mainly by a hormone, a peptide hormone. It's a short peptide hormone. It's composed of about 25 amino acids known as hepcidin or hepcidin. And this is mainly released from the liver. And it is an inhibitor of iron absorption and transport as well, and uptake. So what it does is that it can, so it's released from the liver as a result of, if you have high iron load inside the body, if you have inflammation inside the body as well, these are all inducers of iron. If you have low level of iron, then you will have inhibition of the production of hepcidin. So what hepcidin does is that it is an inhibitor of iron transport. And it acts on a number of tissues, including intestinal cells, and it can also function, or it can also act on macrophage cells. Now, نحكي عنها آخر المحاضرة. هاي pathologies with diseases. Yes, good point. So hepcidin has a number of target tissues or cells. It's released from liver. It can act on intestinal cells. What it does is that it inhibits ferroportin. So iron is not released out of intestinal cells, so it stays inside. Okay, since there's iron overload or a lot of iron in the body, this is inhibited so that it stays in. And if these cells die, then it's okay, it's fine, because there is enough iron. Hepcidin itself can also act on the divalent metal transporter, reducing its expression. So less iron would be absorbed by these cells, and most of this iron would leave our system. Now, it can also act on the ferroportin as well, and on macrophages as well. But it can also act on macrophage cells to reduce the activity of ferroportin, so it stays in. It doesn't leave these macrophage cells. So this is the action on ferroportin. It can also act on divalent metal transporter. I tried to find a figure, I couldn't, but this is a nice research article showing activity or effect on the divalent metal transporter and the ferroportin. These are control cells, no hepcidin, but if you have hepcidin in the system, or if cells are exposed to hepcidin, you have reduction in the activity of the divalent metal transporter, so you have little or reduced absorption of iron, and you have increased activity of ferroportin as a result of the presence of hepcidin. Yes, sir. Reduced activity of, this is not, لاحظ هاي الستار. هاي الستار indicates a significant difference, but slowly it's not significant. So you don't see this. But we already know that hepcidin acts on ferroportin. بس هاي research article بشيء ثاني. It's research anyhow. طيب. So hepcidin is really an important hormone. It can also be regulated by a number of factors. حكيت عن شوي منهم. But one of these factors is anemia. So if you have reduced iron in the system, you will have release of a molecule, a hormone known as erythropoietin. Erythropoietin acts on erythroblasts. Erythroblasts release another cytokine known as erythropoietin. Erythropoietin can act on liver cells, hepatic cells, and it can act via another mechanism to reduce the production of hepcidin, to increase absorption of iron by intestinal cells and release of iron by the ferroportin. Now, there are a number of factors that can act on hepatocytes to induce the production of hepcidin, like the production to increase the release of hepcidin, like iron overload, or certain cytokines like inflammatory cytokines, interleukin-6 as an example. So this is how hepcidin is regulated. So this is what hepcidin does, and this is how hepcidin is regulated. Very quickly, you remember maybe this slide. We talked about it in molecular biology. We said that there is an iron response element in the messenger RNA molecules. And this element, a sequence in the RNA, it is the binding site for a regulatory protein known as iron response element binding protein. Now, if you have iron deficient cells, and you have, and this element exists in the 5' end of the messenger RNA, then you wouldn't have any translation of these proteins, ferritin, ferroportin, and the ALA synthase. But it also exists, the same element exists in the 3' end of a number of messenger RNAs, including transferrin and divalent metal transporter to increase the transport of iron and absorption of iron. So you have stabilization of this, you have more of this. If you have iron replete cells, or if you have iron overload, you have the opposite. That is, you have increased expression of these proteins to store iron, and you have reduced expression of these proteins as a result of that. Okay. هذا الثيروبورتين مش اللي موجود بالintestinal cells، actually بيكون الموجود في الماكروفاجز. Okay. طب نحكي عن iron related diseases. Good point. Right. These are the diseases that we will cover. So we'll talk about hemochromatosis. This is a condition where you have an overload of iron. A lot of iron exists in the system. And it can be related to hepcidin deficiency, or it can be related to ferroportin. Again, it can be quantitative or hepcidin resistance, depending again on the effect. I did send yesterday an email telling you where to go to in Lippincott. Now Lippincott does not have all of the information that I can cover in this lecture. And if you information, I think important لكم تعرفوها. I try not to go into too much details, but I think these are important information. So the main resource for this lecture is, the main resource for you is the lecture itself. Okay, the information that I give you. Now you can go back to Lippincott to just read and enjoy. And we'll talk about iron deficiency anemia. So hemochromatosis is basically a hereditary disease. So basically, it's characterized by excess iron absorption, saturation of iron binding protein, mainly transferrin and the other non-transferrin proteins, resulting in deposition of hemosiderin. I'll show you an image of that in tissues. Of course, if tissues contain a lot of iron, well, that means that you will have a lot of reduction, oxidation, and damage of molecules, and eventually cells die. So it can be toxic to cells. Now, the main cause of the most commonly it occurs in males versus more than females.
And the females different.
Yes, of course, because females lose blood as well. So they are sort of like, males are more susceptible to diseases and symptoms versus females. Now, the primary cause is that you have an inheritance, it's autosomal recessive inheritance of a defective protein known as HFE. Okay? But then you have other 4 genes we'll talk about now that can also be mutated. Now, if you have accumulation of iron, you will have it accumulated in different tissues, and different tissues will be affected, including liver, pancreas. Of course, these are the organs, these are the conditions. So if iron is, if you have iron accumulation in pancreatic cells, this can lead to diabetes, pigmentation in skin, cardiomyopathy in heart, and so on. So depending on the tissue, you will have different effects. So these are the different classes of hemochromatosis. We said that the main cause is a defect or mutation in a protein known as HFE. But you can have other proteins that can be defective, and they're all related to the whole scheme of iron absorption and transport. So you can have defect in a protein known as HJB, you can have defect or mutation in hepcidin or transferrin receptor 2 or the ferroportin, but the most common is the HFE. So what's the idea here? Remember how I said that there are 2 transferrin receptors, transferrin receptor 1 and transferrin receptor 2, and they have different functions. Okay, they can both bind to transferrin when transferrin is bound to iron. Now the idea here is that with transferrin receptor 1, it will be bound with the HFE protein. So HFE is actually an inhibitor of transferrin receptor 1. It's not functional when it's bound. And HFE actually can bind to transferrin receptor 1 through beta-2 microglobulin. So you can have mutations in the beta-2 microglobulin as well. Or the mutation in HFE can affect its interaction with the beta-2 microglobulin. So anyhow, so the idea here is that in the basal state, when there's no iron or very little iron, transferrin receptor 1 is bound with HFE. Now, if there is iron, now there's competition between transferrin and HFE in binding to transferrin receptor 1. Okay? So if there is now iron in the system, iron would bind to transferrin, you have a lot of iron bound to, you have a lot of transferrin bound to iron, and transferrin would win the competition. It would interact more often with transferrin receptor 1 than HFE. Now this would result in uptake of iron by the transferrin receptor via receptor-mediated endocytosis. HFE now is free. Now it's not bound to transferrin receptor 1, so it binds to transferrin receptor 2. When it binds to transferrin receptor 2, it induces a signal. And this signal, what it does is that it induces the expression of hepcidin. Why? To balance the amount of iron that goes into cells. So iron is induced, so cells would, again, balance how much iron goes into them. Now what happens if there is a defect, if there's a mutation in HFE, this protein, then in this case, the transferrin receptor 1 cannot be inhibited by HFE, and you would have a lot of uptake of iron inside cells, and you have accumulation of iron inside cells. That's one. 2, there's no signal in here. It cannot interact with this as well. So there is no production of hepcidin. So that results again in more absorption of iron, more release of iron from intestinal cells and from macrophages, and there will be more uptake of iron inside these cells. So this is how regulation takes place, and most mutation is basically a cysteine is converted to a tyrosine. Why? Because when you have a cysteine, and cysteine can form a disulfide bond within this protein. If there is no disulfide bond, now this protein, the HFE protein, cannot interact with beta microglobulin, and as a result, it cannot interact with transferrin receptor 1. So that's the main mechanism, the main mutation that takes place inside these cells. Okay? So this is type 1. This is the most common one when you have mutation in HFE. But you can have also mutation in other proteins because we have a complex. It's not only a single protein. We have the beta-2 microglobulin. We have another protein known as the HJV. You can have mutations in the hepcidin. You can have mutations in the ferroportin. These are the different types, less common, but different types of mutations that can take place. Regardless of what happens, if you have mutation, and if there is a mutation in HJV or the hepcidin, this is related to what is known as juvenile hemochromatosis. That is, it's a condition that affects young children more often than adults. So it's known as the juvenile hemochromatosis. Okay? So when iron accumulates inside cells, you have these clusters of iron inside cells, and these can be toxic, resulting in the formation of what is known as hemosiderin, which can be stained inside these cells. So you would have something that looks like this if iron is stained. So it's basically iron deposits inside cells, and again, it is toxic. So this is hemochromatosis. Now, the other condition that is related to deficiency of iron is anemia. And in anemia, it's the most common condition in the world, right? And it's related to nutritional deficiency. People are not eating right. It affects, of course, poor countries more than, of course, rich countries. It makes sense. But so that's the main cause. But there are different causes as well. It's not related only to the intake or ingestion of iron, but it has to do with vitamins as well. But regardless of what happens, it can be diagnosed by looking at the size of red blood cells. So in case of deficiency of iron or any other one of those metals, the size of red blood cells will be smaller than normal. On the other hand, if there is deficiency of vitamins, the folic acid and vitamin B12, the cells would look larger than normal. Now, why is it that they look large if there's deficiency of these vitamins? Well, it depends. If there is deficiency in folic acid is important for DNA replication. So cells cannot replicate their DNA, and they would look larger. Not only red blood cells that would look larger, but also you would have the neutrophils would also look large as well. So this is larger than normal red blood cell. Neutrophils can also look larger. So why is it? So that's folic acid. So what about vitamin B12? Why would it cause the macrocytic phenotype? Because vitamin B12 is important for the regeneration of folic acid during all of these reactions. So this is the main reason. So again, you would have stop in DNA synthesis and cell division. And finally, there is a condition also known as anemia of chronic disease. And this affects actually rich countries, people of rich countries, more than poor countries. And the idea behind it is that it's related to infections. So in these countries, you would have high rate of infection, and this infection will be rather chronic rather than acute. And remember that hepcidin is regulated by inflammatory cytokines like interleukin-6. So if you have chronic infection, then what will happen is that a lot of release of these cytokines, resulting in increased synthesis of hepcidin. Hepcidin can act on intestinal cells and macrophages, resulting in reduction of activity and production of the ferroportin and the divalent transporter, and so on, resulting in storage of iron inside macrophages and intestinal cells, and other cells cannot get there, cannot get enough iron inside them. So this is anemia of chronic diseases. So إذا الله هيك فتحها عليكم ورحت على أمريكا وأوروبا, you would see this more often than لو رحت على الهند, for example. Okay? So this is our lecture. Questions? شيء سريع. محلات ممكن ناخذ غياب لو سمحتم. على اخذتوا القوائم الجديدة؟ طيب على القاعدة القديمة اللي انتم متعارف عليها، اللي انتم عارفينها. نعم. لا ما بتعمل رقمك؟
لا بس مواد غير.
انا عندي القائمة الجديدة اللي هي ثلاث الارقام، بدك تكتب لي اسمك. ماشي.